Hi, well, I'm here to give you just a kind of a quick tour through atomic orbitals. And the starting point for this is an equation that you might have heard of. It's called Schrodinger's equation, and it's written this way. This part is the Hamiltonian, h, and this is a Greek letter psi. It goes h psi equals e psi. And so how does that relate to anything? Well, the Hamiltonian part, it's a mathematical object, and it has two parts to it. It has a kinetic energy part, and it has a potential energy part. Together they describe whatever atom or molecule you're working with. Unfortunately, the kinetic energy part involves calculus, and so it's beyond the scope of a general chemistry course. But the potential energy part, that you're well aware of, and it says something like this. If I have a plus charge, and let's suppose this is the hydrogen nucleus, just a proton, and a minus charge, that's the electron, then the potential energy between them would be some constant times the charge on the plus times -1 for the negative for the electron divided by this distance between them. So that's what goes into Schrodinger's equation. Now, because it involves calculus, we don't normally have you solve this equation in Gen Chem, but it's easy enough to solve on Spartan or some other computer, and the result of the solving it is really what you should know about, which is this. After you solve Schrodinger's equation, you get a whole bunch of wave functions, psi's, and energies of each one of those. Okay, and I'm calling it a wave function, but you probably know it by another name called an orbital. So you get a bunch of orbitals and energies out of solving Schrodinger's equation. In this case, let's say for a hydrogen atom was just a proton and an electron. Now what I've drawn here is a sort of superimposed, I have a Coulomb's law here. That's just this equation here, D on the horizontal axis, and then energy on this axis, potential energy. And that's just, I think, to kind of orient you to the sort of forces that are going on. The lowest energy solution that comes out of Schrodinger's equation I've indicated right here, and then it goes up here. So it turns out there's just one orbital that comes out there. It turns out there are 4 that come out here, and there are 9 that come out here. And so part of what I'm going to tell you about is to sort of describe those that come out. Now, every wave function that comes up, or orbital that comes out, it actually has, we have to keep track of them somehow. And one of the ways that we can keep track of them is through these things called quantum numbers. So that one is called the principal quantum number, n, and I've actually labeled this here, n equals 1, 2, and 3. The principal quantum number defines a few things. Obviously, it defines the energy that the orbital or wave function will have. It also turns out to define the shape. The size of the wave function or the orbital. The bigger the n, the bigger the orbital. And it also controls some of the values that the other quantum numbers can have. So let me give you an example. When n is 1, L can't get bigger than one smaller than that, so L can only be 0, and M sub L can only be 0 as well. Now, what do L and M sub L mean? Well, L determines the shape of the orbital, and M sub L determines the orientation. I've drawn here a depiction of this orbital right here. Very okay. When L is equal to 0, we just get spheres. That's the shape of the orbital. And there's really not much to say about the orientation of the sphere. It looks the same whichever way you look at it, and that's reflected in the fact that M sub L is just 0. Let's see, when we get up to n equals 2, that's this second level here, or what we call the second shell. N equals 2. Now L can take on 2 different values. L could be 0 or 1. If L is 0, then M sub L is only 0, and that's what I've drawn here. So this is this orbital right here. Okay, and but L can also be equal to 1, and that's this trio here. You can see that when L is equal to 1, the allowed values of M sub L are -1, 0, and +1. That runs the whole range determined by that, and that's those 3 guys right there. So now we have sort of another idea that's cropping up. M sub L determines the orientation of this orbital, and you can see that they're in 3 different orientations. And L obviously determined the shape of it, because when L was 0, we got spheres, and when L was 1, we got these dumbbells. And we can go on beyond that, but I don't have room to draw the rest of them for you. You probably know the names of some of these types of orbitals. This is a 1s orbital. It's an s orbital, and the 1 means n equals 1. Here's a 2s orbital. That's because it came from n equals 2, but it's a sphere, and which is equivalent to saying L is equal to 0. Here we have, they're all n equals 2 orbitals, but this is, they're p orbitals now, so we would call this a 2p. This would maybe be a 2px, and a 2py, and a 2pz orbital. There are 3 of those, and you can see that that coincides with there being 3 values of m sub L that are allowed there. So now, finally, why do we only get 1 orbital here? Well, that's because of the restrictions on L. Why did we get 4 here? Well, L could be 0, in which case we get 1 orbital when L is 0. That's that orbital. And when L is 1, m sub L could be -1, 0, and +1. Those are those 3. So these 4 orbitals right here are the 4 in the second shell. And if you think about it, how about the number of orbitals in the third shell? Well, we'll have a single s orbital, we'll have 3 p orbitals, and then we'll have 5 of the next set of orbitals, which are called d orbitals, adding up to 9.